Hi everybody. So we are in the Hope College production studio for this video, and what we're going to do is we're going to do a rope problem, and I'm going to break it into two components. So we're going to take a problem where it's going to be all the rope to the top, and then we're going to take where we take half the rope to the top. So we've got a 60-meter building. This really isn't all that relevant, other than it makes sure that the 20-meter rope that we're working with is dangling and it is not ever laying on the ground. So the 60 just sort of falls off the way, and it's just information to help us make sure that we don't have rope on the ground. The density is going to be 2 kilograms per meter. That's the density portion of the integration that we're going to be working with. And we're going to be talking about giving the scale or the axis going from 0 up to 20. All right. Now, the density is going to be 2. The gravity, remember, will be 9.8. Really, it's negative 9.8, but as we discussed, we take the positive of it. The distance in this case. The distance in this case is going to be 20 minus y. So if you start thinking about it, when your y is 0, the distance that piece has to travel right here is 20 units. If your distance or your y value is 10, then the distance that has to travel is 10 units. So I wrote that here. So when y is 0, so you're down at the bottom of the rope, the distance that piece moves is 20 meters. And so 20 minus 0 gets us that correct length. When y is equal to 10, the distance that the piece moves is 10 meters. And again, we get the correct length. So yes, 20 minus y works as our distance component. We want to have all of the rope, and catch that, I want to have all of the rope, so 0 to 20, get up over the wall. So we want it all up over here. So we have our density component, we have our gravity component, and we have our distance component. So 2 times 9.8 times the integral of 0 to 20 of 20 minus y dy. So that's going to get us to 19.6. When we take the antiderivative, we get 20y minus y squared over 2. And when you plug zeros in, those go away, so we just have to think about the 20. So we get 400 minus 200. So that's going to be 200 times 19.6 joules. And when you multiply that, you get 3,200 joules. Now, what would happen if we just want the top half of the rope? So you're kind of thinking about this as the top half of the rope gets put over and the bottom half of the rope just gets sort of drug up to the top. So the key here is that the only stuff that's getting moved up and having some sort of change is the stuff from 10 to 20. And so you still have the distance component in there, but you're only moving up over the wall everything that's from the 10th unit up to the 20th unit. Now, the things that are going from the 0th unit to the 10th unit, they are all moving a distance of 10, but they are not getting pulled up over the wall. So this is the distance. Every piece that's down here gets moved. It all gets slid up 10 units. So that's why there's a 10 there. And then we have our 2 times 9.8 again. And we integrate from 0 to 10 because the stuff from 0 to 10 is all the stuff that is getting, here's our 0 to 10 is all the stuff that's just getting slid up, and it would be sitting in this space, okay? Now, you could think about it as getting the mass, which is 10 times 2, because it's a 10-meter long piece, and 2 as it's 2 kilograms per meter, so that's our mass. And then we could get our force by tacking in the gravity, and then recognizing that we're just moving at 10 units, and so that's where our distance is. And it works out, that's what the integral will give you. And then this integral here is similar to what we did up above there, and I trust that you can crunch that out. So I hope that helps. All right, I will talk to you guys.